around and helping. Well, I don't think any of us were. Mm, yep. All right. Well, I've just got to tell you, today is going to be the hardest day of the whole semester. Well, you all know why it's hard, right? Because you're really not here. I mean, popping plastic. I mean, come on, let's face it. If we all could get our plastic out and start popping it, we'd go nuts. I mean, and frankly, most of you are thinking about what you're going to be doing in 2 days. That's right. I mean, everyone got their stretchy pants picked out? No? If you haven't got your stretchy pants picked out, you need to go pick out your stretchy pants. Then you need to go buy a pair. You've just got to put on stretchy pants, and then you got to eat as much turkey as you possibly can get your hands on. If you're a vegetarian, well then, eat your tofurkey. Yeah. What we're going to talk about today is not really actually all that difficult, although it's the part of the kidney that everyone stumbles over. So even though I am saying it's the most difficult because, yeah, it's hard to show up on a Tuesday before, well, a holiday, it actually is kind of the tough stuff. But once we do today's lecture, everything else is downhill. It's all easy. All right? So, remember we were talking about on Thursday? Thursday, we were talking about the different mechanisms, or the different mechanisms that the kidney uses in order to create urine. And so we had talked about the process of reabsorption, getting the materials the body wants back to the body. So today we're going to focus on the other two, and then we're going to actually look at how we actually make urine, and then we're going to deal with buffer systems. That should be the gist of everything. And so the next step beyond reabsorption is secretion. And what secretion does, it allows the kidney to actually get rid of excess material. Or you can think about it this way, it gets rid of material faster than it would if it just did filtration by itself. All right? So remember we looked at filtration. We said filtration is when the blood travels through the glomerulus and it pushes that 20% of that plasma out, and so that's how we can get stuff out of the body. But there are times when you need to get rid of other things, and you need to get rid of things faster. Now, the two simple things to get rid of are really, really itsy-bitsy, teeny-tiny. We're talking about protons, we're talking about potassium. All right? So there are times when you have excess of potassium, there are times when your blood is too acidic, and so you just need to get rid of these things. But in order to do this, you need to have some sort of transepithelial transport to move that material from the blood through the tubular cells and into the tubules. So at some point, you're going to have some sort of active process to allow us to do that. All right? So there's going to be some transepithelial transport. Now, protons moving acids out is done at all levels. It can occur in the proximal convoluted tubule, the distal convoluted tubule, or even in the collecting ducts. Doesn't matter where it's going to happen. It can happen anywhere. And it's dependent solely upon the acidity of the blood. The greater the acidity, the less protons you want, so get rid of them. All right? That's a real simple mechanism. You can pretty much understand that. Potassium secretion, on the other hand, is a little bit more complex because in the proximal convoluted tubules, we're actually reabsorbing potassium. All right? And so when we're talking about potassium secretion, this is going to be occurring here in the distal convoluted tubules. So proximal, we're reabsorbing. Distal convoluted tubules is where we're actually going to be seeing the process of secretion. All right? And it's an easy process. I mean, you can think about it like this. When I have higher level of potassium in the blood, what's going to happen is I'm going to move that down its concentration gradient out into the interstitial fluid, and then I'm going to use the sodium-potassium ATPase pump to pump it into the cells against its gradient, and then it's going to move once again down a concentration gradient out into the tubule. Real simple mechanism. All right? But how do we do this? How do we increase the probability that this is going to happen? Well, simply put, we have it under control of a hormone that we've already seen. Oh, actually, we haven't seen this one yet. That's right. Different class. We talked about this in another class earlier. It's aldosterone. All right? Now, aldosterone actually has dual roles, and we'll learn about what aldosterone does a little bit later beyond just potassium secretion. But what aldosterone does is it basically tells those tubular cells start making more sodium potassium ATPase pumps. And so what happens is that aldosterone levels are going to increase. That's going to increase the rate of tubular secretion in response to an increase in plasma concentrations of potassium. And at the same time, it increases sodium reabsorption because we have the sodium potassium ATPase pump. As a result, we get rid of more potassium, but we hold on to more sodium. Now, if we hold on to more sodium, what else are we doing? We're holding on to more water. Now, you're going to see this, and we're going to see this a little bit later, and we're going to look at all that top stuff, and you're just like, oh, yeah, okay, now I got this. This system is easy. Right? But this is secretion in a very, very simple nutshell. The harder stuff with regards to secretion has to do with organic ions. Now, many of you are planning on pharmacy, right? Or at least some of you are planning on pharmacy? No? No? Okay. We got a couple that are going to be doing pharmacy. And each of you have, at some point in your life, have taken a drug, right? I mean, at the very least, you've taken an aspirin, right? And if you've had a headache before or you've had a fever for an extended period of time, you take yourself a Tylenol and you have to sit there and stare at the bottle until you can take another one. How much later? 6 hours, or most of them it's 4 hours. I think they've now changed it with Tylenol because of toxicity issues and people overdosing themselves. You know, but it's basically you sit there and you're going, still got a fever. When can I take it again? 4 hours. Well, what we're talking about here is how quickly we can remove the metabolic byproducts of Tylenol. Now, what happens is the body breaks down Tylenol and it produces all these little tiny organic ions. And while some of them can pass through by filtration, there's a system in place that allows you to pick up these organic ions and move them through the process of secretion. This is also the way that your body gets rid of other organic ions that it produces to increase the rate at which you remove these metabolic byproducts out of the body faster than you normally would. And what I'm trying to do here on the little picture is to kind of try to show you how this works. And again, you already know the mechanism. This is the law of mass balance or the law of mass action. And in essence, what I'm trying to show you here is we're removing a hormone, all right? And so, or some sort of signaling molecule. And so let's say that we have a carrier molecule where we have this perfect balance, once again, 2 off, 2 on. And this is our perfect ratio. And so all we got to do is maintain this ratio in order for our body to be happy. And so what happens is as it gets filtered, those molecules are not bound to the carrier, get filtered through. And so now we have our carrier completely bound, which now violates our law of mass action, which says we want a perfect ratio. And so one of our little ions pops off, and now we're back to a perfect ratio. All right? But now the blood is moving through the peritubular capillaries where it comes into contact with this secretory system. And here, once again, we can take our unbound one and we can move it from the peritubular capillaries into the tubules. All right? Transepithelial transport to do so. And then now we have imbalance in our system once again. And so what we have to do is we have to, well, we can't split the molecule in half. So we have to spend half our time on and half our time off our carrier. All right? That's how we solve the problem. All right? And so when it falls off, well, maybe it can be picked up. And if it gets picked up, well, voila, well, look what we've done. Instead of just moving 2 into the system, what we've done is we have removed twice as much. Now, I'm just using this as an example. It's not always twice as much. It's not, you know, a perfect system like I've described here. But in essence, what it does, it shows you the rate at which you're able to remove things faster than you would if you solely relied on filtration. Does this make sense? Kind of, sort of? Yeah. Well, so the carrier would never be able to come through because usually the carrier is probably some sort of protein. And so the idea is that the carrier stays out here in the blood and is just traveling around. And so really the only things that are being filtered are really the unbound metabolites. And so these are things that are small enough to actually even be filtered themselves. So we're not talking about a full-blown protein. We're talking about something that's been broken down. And so part of the way that you protect your body from these horrible, nasty things is you bind them up with some sort of carrier molecule in the blood. All right, until you arrive in an area like this where you can filter that stuff away. Does this make sense in terms of what you're trying to accomplish? Okay. Seeing a couple noddings of the head. All right. So really what we're doing is we are increasing the rate of I should say, removal. All right. So instead of secretion, let's say it increases the rate of removal from the blood. And so it's a way to get rid of things that could be harmful to you. All right. This system is localized to the proximal convoluted tubule. All right. Now, to make this a little bit easier to understand, I want you to think about plasma clearance. All right, and that's why I mentioned the drug, because this is one of the things that pharmacists do and tell you about. The reason you take these drugs at specific times is because if you take them too soon, you can't remove the metabolites fast enough from your body, and so those toxins begin to build up in your system and can cause you harm, which is part of the reason why Tylenol is under assault right now, because they have the dosing levels too high for the clearance rates. And so people would actually they dose themselves normally, but they would go, if you look at the bottle, it says you may take these 2 pills every 4 hours for 24 hours. You know, it says never take more than 6 of these pills in 24 hours, right? And part of the reason is because those toxins start building up. Anyone here like vitamin C? I mean, you go down to Walgreens and buy the 600 tablets of 500 milligram vitamin C's that taste like orange tablets because it's basically like, oh, I don't know. You know, it's citric acid, but it tastes like candy. You know, and you know how much vitamin C you can take in a day? Anyone ever? Yeah. It's 3,000 milligrams in a day. Yeah, you can't. If you take 3,000 milligrams, it's going to take a while, but it doesn't do you any good. I mean, your body only absorbs a certain amount that you can use. The rest of it, there's a joke on. See, I'm just all over the place today. There's a joke on Big Bang Theory where Penny and Sheldon were. Yeah, you're making just expensive urine when you're buying vitamins because your body doesn't use and you just pee it out. And he says, "Oh yeah, if maybe that's what I wanted, Sheldon. Oh, in that case, you want manganese." You know, he's looking. That was funny, but I mean, in essence, you know, that's over 3,000. Then vitamin C starts becoming harmful because you can't remove it fast enough from your body. All right, and what we're talking about here is we're talking about plasma clearance. How fast can I get this stuff out of my body so it doesn't build up to toxic levels? And the way plasma clearance works, it's the volume of plasma that's being cleared of a particular substance. It's not how much substance is in the plasma. All right, so you're talking about a volume of plasma cleared per minute. All right, so every substance has a different plasma clearance rate. The good news is you don't have to learn this. Bad news, pharmacists, you do. Not for my class, but in the future you will. All right, and what it does, it basically demonstrates the effect that excretion has on removing this stuff from your body. Now, I'll give you an example of a way that you can cheat this system. And this is for those of you who are going to be suffering from flu, and high fever in a couple of weeks because, well, it's that time of year, right? And finals are coming up, and that's when it's all going to happen, right? So let's say you have a fever and you take Tylenol. The next time you can take the next Tylenol, if you go look at the bottle, really it says 4 hours, but I mean some of them might say 6, all right? Well, what you can do is after 3 hours, you can go and take ibuprofen, all right? And when's the next time you're allowed to take ibuprofen? Anyone ever looked on the side of a bottle? 6 hours, right? But because ibuprofen and Tylenol are 2 different drugs and 2 different chemicals, you can actually take them concurrently, right? Because they each have their own individual clearance rates because they're each own individual molecules. And so what you do is you take Tylenol, take ibuprofen, Tylenol, ibuprofen, Tylenol, ibuprofen over and over again. So you can basically dose yourself every 3 hours instead of waiting every 6 or every 4 or whatever it is. And you can keep your temperature at appropriate levels. Now, you'll learn this when you have children. All right, because there's nothing worse when a child wakes up at 4 o'clock in the morning screaming because the medication has gone off, and you're like, now you have to sit up, so you learn, okay, I've just got to dose and dose and dose. So, all right. Now, plasma clearance is actually really, really simple if you think about it like this. What am I trying to accomplish, and what does plasma clearance tell me? And so, if the plasma clearance is only about how much a substance is filtered, then your plasma clearance rate will always be equal to the glomerular filtration rate. All right? So if all I know is that this substance is going to be filtered, then I know that its plasma clearance can only be as fast as whatever my glomerular filtration rate is. If my substance is both filtered and reabsorbed, then it's going to be less than the glomerular filtration rate. Now, an easy example of this is to think about glucose. Your body wants to hold on to glucose, but it still filters it, but it reabsorbs 100% of that glucose back into the body. So the plasma clearance of glucose is effectively 0, and is that less than the filtration rate? The answer is yes, because filtered equals filtration rate. All right. Urea is another example where you actually have less of a plasma clearance than you actually have with regard to the glomerular filtration rate, because a portion of urea is actually reabsorbed. It's just done slowly, and so some of your urea leaves the body, but some of it stays in the body. All right. When a substance is filtered and secreted, then the plasma clearance rate is going to be greater than the glomerular filtration rate. And this should be really simple to think of. If filtration is my glomerular filtration rate, if I'm adding more things into the filtrate, then I'm obviously getting rid of it faster than I can filter it. All right? And that's what each of these things. And so an example that they use here are protons, but you can say penicillin, for example, is picked up and thrown through the process of secretion as well as being filtered through. So I get rid of penicillin faster than I normally would if I just filtered it. So understanding this concept is going to be helpful with regard to those who are going into pharmacy. Now, for those who are planning on medicine, you're going to have to learn this in a very vicarious way and pretend like you know stuff. And then you write your prescriptions and pretend like you know what you're talking about. Sorry. I'm trying to be silly. It's hard on a Tuesday right before everyone goes home. A physician is just a well-paid plumber. I love telling this to my friend who is also a cardiovascular surgeon. He looks at me, shakes his head. I say, yeah. What did you do today? Well, I sealed a pipe. Yes, you did. First off, understanding what the bladder is. Bladder temporarily stores urine. Remember, we're always making urine, but we're not always excreting urine. Right now, many of you have been drinking for a while. You rushed to class. You decided to forego visiting the restroom, and so right now, your body is starting to tell you, hey, psst, psst, hey, psst. Go. And you're saying, no. You will wait when I tell you. And so you're kind of kicking back and waiting. Now, the reason it can serve as a temporary storage site is because of the way that it's constructed. First off, the epithelial cells themselves actually can absorb or place more surface in their surface area. In other words, they can add to or subtract from their plasma membrane. It's called membrane recycling. So in essence, what they do is they take vesicles and join them up to the plasma membrane, which increases their surface, or they take portions away, when they're smaller. So that means as the bladder fills, the cells themselves actually get larger. All right. The smooth muscles themselves actually stretch without building up tension. We've talked about all these other systems, like when blood goes through a blood vessel, when you get pressure, the response is to fight back. All right. Here, the smooth muscle just kind of relaxes, like you haven't learned that yet either. The stomach relaxes and does the same thing. This is why you can eat 16 pounds of turkey. All right. This makes more sense to ladies than to guys because you understand fashions. The bladder wall is folded like a pleated skirt. What do pleats look like? Kind of. Over and over again. Yeah. When the bladder begins to expand, those pleats come undone. And so now what was small is much, much larger. All right. What created very little, what appears to be very little surface area is now much, much larger. All right. And lastly, we basically have parasympathetic fibers that cause the bladder to contract, presuming, of course, that the passage to the urethra is open. Now, you've all experienced this, right? That's when you have the urge, all right? Now, the urethra is that tube between the bladder and the bathroom, or your toilet, or whatever you want to call it. For guys, nature is our toilet, so it can just be anything. All right, now there's two sphincters. We have the internal urethral sphincter and the external urethral sphincter. The internal urethral sphincter is smooth muscle. It's part of the cell or the bladder wall. And so as the bladder begins to expand, that muscle begins to relax. And so when the muscle of the bladder begins to contract and cause pressure on the bladder, it's basically allowing that fluid to go beyond that sphincter and say, all right, I'm ready to go. But it's the external urethral sphincter that you have control over. It took you 2 years to learn, or a little bit less, how to use that muscle, and you're not going to let go of that until you've drank too much or you become old. Really old. All right? Here is where you have voluntary control. And so if I said no one's allowed to leave here, but everyone has to drink a gallon of water, you guys could probably sit here for some time holding it, right? And you might dance a little bit, you know, do the cross, well, you can't see, crossing of the legs, whatever it takes. But in essence, what we're doing here is there are motor fibers that are constantly firing on the skeletal muscle. Remember, why would we always be firing on skeletal muscle? Because it's voluntary. And what do we know about action potentials on skeletal muscles? Are they, or fibers on skeletal muscles, are they excitatory or inhibitory or both? They're only excitatory. Remember, if I want a contraction, I have to think about and force the contraction. When I want to stop the contraction, I stop. All right, muscle goes back into place. All right, and so that's what's going on here. They're always excited, and so all we got to do is stop that signal, and then the external sphincter relaxes, and then the fluid flows. This is what it looks like. Bladder begins to fill. Stretch receptors within the bladder start saying, hey, you know what? Psst, it's time to go. So they begin acting on the motor neurons that are responsible for regulating the external sphincter, and they begin to tell them, you know, stop. All right? But because these are under voluntary control, we can actually override them. All right? But meanwhile, parasympathetic fibers are going to be stimulated that are going to cause the bladder to contract, which is ultimately going to cause us to go to the restroom, presuming, of course, that we relax our external sphincters. All right? If we do not, if we voluntarily contract our external sphincters, no micturition, which is the fancy word for peeing. Tinkling, whatever term you want to use. And that's what I'm just showing up here. That's all the little balloons. See, they even did that sweet. They used the balloon and everything. Yes. That's a very good question. If you can't hold it anymore, obviously this pathway is prevailing, right? And if your stretch receptors are very, very active and they're blocking this, then your external sphincter is going to relax. That's incontinence as an example. That's a good question. Everything so far pretty simple. Now we know how it happens. Let's see why it happens. All right. Now, I want to point out that your body has a natural osmolarity. It's about 300 milliosmoles per liter, and that's what we would consider to be isotonic. So 300 particles of solute per liter of water, 300 milliosmoles, I should say. If we were to say that we had a solution that was hypotonic relative to the body, is that more or less in terms of milliosmoles per liter? Less. And so what does it mean about the water? How much? Too much, too little? Too much. So given that, that means hypertonic would mean you'd have more than 300 particles or units per liter, and then this would be too little. I do this because it's a good exercise to remind yourself what osmolarity is, because very often this is how we talk about stuff. Now, understanding this will help us to understand how our body works, because we know that in order to remove something from a system, we're going to have some sort of gradient, right? So if we want to get rid of excess water, or if we want to hold on to water, then our osmolarity needs to be different than the osmolarity of that fluid. All right? In other words, we have to have some sort of imbalance. If we want to have a way to get rid of excess water, we better have excess water to get rid of it. If we want to conserve water, we need to have a way to hold on to it. All right? I know that seems almost silly to say. It's like saying if you want to draw something with crayons, you have to have crayons. But you need to understand our starting point here. Now, where we get our water from? We either eat it or drink it, right? And then when we get rid of water, it's not solely through urination. We actually lose a lot of our water through our skin and through our lungs, as well as defecation and urination. All right? So there are a lot of ways to remove water from our body. All right? A lot of ways to put water in our body. All right? Now, if your water level gets really, really high, your kidneys are already designed to get rid of excess water. Yes. Pooping. That's a fair question. Yeah, this is what the latter half of this class is. It's all about our basic needs. Pooping, peeping, peeing, and sex. That's everything we need to do in life. It's all right here. Oh, plus eating, because you can't really poop without eating. So this is like caveman section. All right. Now, the kidneys themselves are already pre-designed to get rid of excess water. All right. We're going to see how this works. All right. But if you lose too much water, you cannot return water back to your body through your kidneys. All right? So what we have to do is we have to have a way to reclaim water before it's actually excreted, before it gets to the bladder. Because remember, the bladder is really already on its way. It's gone. Remember we said that very second slide on the very first day of class was, once urine is made, it cannot be changed. So once it leaves the kidney, whatever you've done, you've done. So if all of a sudden you become dehydrated and you've been making watery water, you cannot, or watery pee, you cannot reclaim that water from the pee. Yeah. There you go. But see, that's different though, because then you're putting it into the cup or the mug or the bark or whatever he puts it in, and then you're putting it back into your body. I can't believe he does that. Yes, it's sterile, but that's sterile in the bladder. Once it starts passing through the urethra, you're talking about like the land of every microbe on the planet. It's true. Bladder infection. Yeah. Because they're just like, party. Right? I mean, that's what the microbes do. They're like, woohoo! Warm, food, sugar, everything I need. We're going to talk about, well, no, we won't. But. Anyway, what we have here is a picture of the kidney. And one of the features of the kidney is that there is a concentration gradient that has been established in the renal medulla. And so what this cartoon is trying to show you is like, look, the cortex is like the rest of your body. It has the same osmolarity as everywhere else in your body. If I go take a sample of brain fluid, cerebrospinal fluid, it's going to have the osmolarity of 300 milliosmoles. If I go take fluid out of the small area out of your toe, it's going to be 300 milliosmoles. If I go and draw blood anywhere in your body, 300 milliosmoles. If I go to the cortex, 300 milliosmoles. But once I get into the medulla, what we have is we have an osmotic gradient that allows us, that has been established, and allows us to create urines of varying concentrations. Now, I think I asked this class, I may be wrong because like I said, I'm dealing with two classes that are about 3 lectures apart, and the lectures are like flip-flop. So sometimes I forget do I ask which questions. What does watery urine look like? Clear. No one ever says it looks like water. I mean, it does. It's clear, right? What does concentrated urine look like? Dark yellow, orange. See, notice the guys are really quick on this because we're just watching it being made. You know, ladies, you have to get up and you have to turn around and look down. And I think at that point you don't even care. It's just like, let me just flush and get out of here. All right, we're just proud of ourselves. Woohoo! All right. So what we're basically saying is that we can create a urine that has a variation in terms of its osmolarity. We can create a urine that has 100 milliosmol concentration, which is very, very dilute, or we can make one that has a 1200 milliosmol concentration, which is very, very concentrated. All right? And this is solely going to be based upon our body's needs for water. How much water does the body need to hold on to? All right? It's your state of hydration. Now, the way that this is accomplished is through what is called the medullary countercurrent mechanism. And this is done or is accomplished through the loop of Henle. Now, remember, the loop of Henle is what originates around the boundary between the cortex and the medulla, and you have two limbs. You have a descending limb and an ascending limb. All right? And these basically run side by side. This is why it's called countercurrent, because it goes down and then it comes right back up right next to it. All right? So ultimately, these two fluids are going to be running side by side with one another. I failed to start recording this. All right. Anyway, this loop of Henle is responsible for establishing this osmotic gradient. All right. And it does so, and it uses this gradient, the kidney uses this gradient to create that urine of varying concentration. It does so primarily through the collecting duct, because the collecting duct travels right back down through this osmotic gradient. Now, what also is important to this osmotic gradient is the vasorecta. All right, and that's not shown in this picture because it just makes things confusing, but we'll see it again. All right, and the purpose of the vasorecta, remember when we looked at it on Thursday, it looked like a bunch of low-hanging capillaries that just kind of looped alongside it, kind of like this, you know, and kind of did something along those lines. The vasorecta is a capillary system that works just like the peritubular capillary system, except its primary function, because of the way that it's shaped, preserves this gradient. Makes sure it doesn't get broken down. All right? Now, very often people ask me, well, God, what do I have to know about this? Do I have to, because we're going to walk through and we're going to see how this works. And I'm not going to ask you and say, tell me how it works, because that's an essay, right? But I want you to understand this because it's a really interesting mechanism that the body has engineered to ensure that you have ways to get rid of excess water, but at the same time figure out a way to conserve it by not expending too much energy. Now, in order to understand that, we need to understand that the two limbs have varying characteristics. All right? And so we're going to start on the ascending limb side because it makes more sense, and then we're going to move to the descending. But remember, D comes before A in our alphabet in the kidney. I don't know why. All right. Well, we're going to descend first. All right. So, in the ascending limb, what we have is we have tubular cells that are completely impermeable to water. And what they have is they have a mechanism to actively transport out sodium chloride. And so in essence, what's happening in the loop of Henle on the ascending side is we're reabsorbing sodium chloride. On the descending side, our loop of Henle is completely incapable of reabsorbing sodium. In other words, there's no mechanism like we saw on the ascending side. But we are permeable to water. And so the way that this is going to work is that as sodium is moved out, we're going to balance that sodium by water moving out. All right? So in other words, the reabsorption that we talked about in the proximal convoluted tubule, where we said water always follows salt, it's true here, except that water can only come out one side and salt can only come out one side. Does that make sense? All right. Now, what I have here are probably 3 or 4 different slides that are just kind of repeating themselves. And in fact, the one thing that I probably forgot to do is there's a flash video that I have that I probably didn't load up. I know I didn't load up, so we're not going to do it. But I'm going to have it on VNet, and you can watch it. You know, and it has the guy droning on, reading the bottom of the whatever it says as you're watching it happen. But I want you to think about what's going on here. What we have is this right here is, let's pretend for a moment that all the fluid in the kidney and in the medulla is osmotically balanced with the rest of the body. All right, so everything is 300 milliosmoles. But what we have to understand is that as the fluid is moving through, you know, we're going to start seeing a change in the properties of those fluids because of the activity of what's going on. On the ascending side, we have all along its full length is you have these pumps that are actively pumping out sodium chloride. When you actively pump out sodium chloride, it causes the osmolarity here in the extracellular space to increase. All right? And so all these would increase, say, up to like 400. And then to balance out that increase in osmolarity, where's water going to come from? Out this way, right? And so if water leaves the tubule, what happens to the osmolarity inside here? It increases as well. Now, this increased osmolarity then moves over to this side. And then what we're going to do is we're going to pump out salt, which causes the osmolarity inside that area to do what? If I'm removing solute from something that has higher solute concentration, what's happening to the osmolarity? It's going down. All right? And then we're going to start moving water out on this side to balance that. And so as we move up this direction, our fluid becomes more dilute. And as we move down this direction, our fluid becomes more concentrated. All right? That's what that says, concentrated. All right? And in the process, what we end up doing is we end up creating this gradient in the middle. And so as the fluid begins to enter, it matches the environment, but as you start progressing down towards it, you become more and more and more concentrated because you're trying to balance out with the environment that's out here. And as the fluid is beginning to leave, what started off as very, very concentrated down here at the bottom becomes more and more dilute. So by the time the urine leaves, or the filtrate leaves the loop of Henle, it is far more dilute than when it started. All right? In other words, what we're saying is that as the fluid enters in through the loop of Henle, it becomes concentrated about fourfold relative to where it started. It goes from about 300 to 1200 milliosmoles. But by the time it leaves, it's far more dilute. In essence, my filtrate is mostly water. That makes sense? So what have we created? A mechanism to get rid of water, which is what our kidney is really designed to do. If we put too much water in our body and we've got to maintain our water-salt balances, the easy thing to do is get rid of water. And that's what our countercurrent mechanism is designed to do. Create a way to create watery pee. Now, the problem is that we don't live in an environment that's always exposed to excess water, right? We have an environment that varies, and we have activities that cause us to vary. You know, some of you brought your water in because you have to hydrate, right? If you go and work out in the yard, what are you going to need to do? You basically sweat all that water out, and so you have to hydrate, right? But if you drink a gallon of water, you've overhydrated, and so now you need to get rid of the excess water. And now we have a mechanism to do so. The excess water we can get rid of because we have a whole bunch of excess water already primed to leave the body. All right? But at the same time, what we've done is we've established this gradient. Remember, the purpose of the loop of Himmel is to create this osmotic gradient inside the medulla. And what we're going to do is we're going to take advantage of it. All right? Before I go on and explain how we're going to take advantage of it, I want to talk about the vasorector really briefly. In a normal system, if you and I were designing a system, here we have our kidney. Coming into the kidney is our artery. Exiting the kidney is our vein. And then if you and I were designing it, we'd say, okay, here's our artery, go in, and we're going to deal with all our things within that cortical, not the radial vein, but the arcuate artery, right? And then what we would do is we'd say, all right, well, you go up, and then here you are, and here's your peritubular capillaries are coming down, they're coming down. And if you and I were designing it, and we wanted to get the blood out, what would we do? Shortest distance between 2 points is a straight line, and we'd go over here, right? Would you design it that way? Yeah, because we're lazy, right? But what would happen is remember, we created this gradient here, right? And if this was my capillary system moving through, and what I did was I basically am moving through an area that has, remember, my blood has an osmolarity of 300, right? So as my blood goes through, what's going to happen is that excess salt that's sitting out here in this space is going to go where? Into my capillaries. And the excess water that I'm carrying in my capillaries is going to come out here and try to balance out this concentration gradient. So while the salt goes into the blood, water comes back out. And so what's going to happen to the blood if I just went straight out? What's that blood going to have? What type of osmolarity? It'd be high. So that's bad. Don't want to do that. In other words, what would happen is for all that work we just did to create this osmotic gradient, if our blood just basically went all the way through and came all the way through, then we would have destroyed our gradient because we'd be drawing the salt out and putting the water back in. So it'd balance everything out, and then we would have no osmotic gradient. So not helpful. But the vasorecta solves that problem because remember, it comes down and then it goes down, it comes back up. And so as salt goes in, because it is a capillary system, and as water comes back out, as you travel down, water comes out. When you come back up, what's going to happen? Water is going to go in, and salt's going to travel back out. And so the osmolarity that comes in is going to match the osmolarity that comes out, or vice versa. And that's what this picture is trying to show you here. It's saying this over here is what it doesn't do. This is bad. Okay? Because if we did all that exchange, that blood would leave with the same osmolarity, and at the same time it would destroy all this as it was going out. But instead what happens is that the blood does increase in terms of its osmolarity, but by that time it leaves, it's normal again. And so what the vasorecta does, it allows for the exchange of materials, and it preserves that environment by allowing those solutes and that solution to go through the exchange process that you'd expect between the plasma and the interstitial space, and then happen once again as the blood leaves. Now, didn't I tell you this was the difficult stuff? Yeah.
So, on that the blood leaves, does it leave the same amount of
It does.
Does it have different
Does it have different what channel? No, it's exactly the same permeability that you'd expect. So it's just like any other kidney or any other capillary system. The only place where we're going to see the fenestrations or the increased permeability is going to be at the glomerulus. All right? And so remember how we described it. We said we have the afferent arterial, we have our glomerulus, we have our efferent arterial, and then I said we have that peritubular capillary system. Well, the vasa recta is a peritubular capillary system. All right, and what happens is that in this case the vasa recta comes down, goes back up, joins up with a vein or a venule, and then ultimately comes through a vein system, and then leaves through the renal vein. So it's going to come back out, but remember we have no exchange between the veins and the arteries and the interstitial space. It's always at the level of the capillaries. So traveling back out through a vein, not a big deal. Traveling back out through a capillary, bad. And that's what we're doing, is by using this system, we maintain our osmotic gradient. If we did something like this, we'd be very sad. Just as an aside, I'll never ask you this, but just as an aside, if you're one of the reasons when a kidney fails, the reason it fails is that you lose the osmotic gradient, and once you lose the osmotic gradient, it cannot be reestablished. So that's why it can't work. Mm-hmm. Yeah. So this is all created during development, and is maintained throughout your life. And once it goes, it never comes back. But that's okay. We have two. Yeah.
So when someone gets a kidney transplant facility, they have to fuck it.
Mm-hmm. Right, and as you can imagine, a healthy kidney to have all this in place, and then the transplant takes place within a very short period of time, and that's always a relative term. That's right. Or you cook it, one of them. Mm-hmm. It can, but remember what you do is you usually put once you remove a tissue, you're going to put it into an environment that is actually going to decrease metabolism at a very, very, rapid rate, so that you're actually maintained at a very, very low metabolic activity. I have no idea what length of time you're talking about here. If it's 24 hours, 48 hours, 12, but once you've lost it, you've lost it. I think the dialysis has to do primarily with filtration rates, but I may not be. We're now going into the land of pathology, which is well unexplored by me. It's like, yeah, I'm like a shut-in when it comes to pathology. Yes. Uh-huh. Mm-hmm. Uh-huh. So one, a referred pain. The vision problems, I wouldn't know why. That's interesting. But again, you're asking the wrong person. If you want me to tell you the molecules that might be involved, well, I wouldn't know the answer to that either, but I could pretend. And no, I don't know. I mean, is it one of the things, is she diabetic? Because, no? Okay. That would be my one. Mm-hmm. Okay. There you go. And we're going to see how this is all maintained here in just a second. Now, does the vasa recta make sense? Yes? Okay. Let's see how this works and why we use this. All right. What we're looking at here is we're looking at the collecting duct. All right. So remember, we went down through the loop of Henle. I'll use my standard. Here is Mariolus proximal convoluted tubule, loop of Henle, come back out, and then collecting duct. All right. And what we said is here's our medulla and our cortex. Our collecting duct, notice, goes right back down through the medulla, and is obviously going to join together with other collecting ducts to form the pyramids, where the urine that's being created kind of accumulates together. All right. And what happens is that This region here, through the distal convoluted tubule, the collecting ducts, are impermeable to water, except under the activity of vasopressin. Vasopressin's other name is antidiuretic hormone, ADH. And what vasopressin does is it acts on the cells of the collecting ducts in the distal convoluted tubule and tells them, through a signaling mechanism, oh, those storage vesicles you have, yeah, the ones I told you to make a long time ago and put away over here, what we want you to do is we want you to take those storage vesicles and move them to the surface of the cell. Because in doing so, what you're going to do is you're going to put aquaporins into the walls of the tubular cells. In other words, a cell that is impermeable to water becomes permeable to water because we're going to put the channels in place to allow water to pass through. Very, very quick. It's through a, what do you think? Well, it says, yeah, it's through a G protein coupled receptors. Yeah, cyclic AMP, second messenger signal. I'm telling you, once you learn G protein coupled receptors, the answer, it's just, if someone asks you, how does this regulate just G protein coupled receptor? 9 times out of 10, you got it right. All right. Impress your professors in medical school. G protein coupled, sorry, it's tyrosine kinase. Ah, well, whatever. All right. In essence, what this does is that when your body wants water back, all right? Remember, we have excess water in here as water is going through. If we want excess water back, all we have to do is create a mechanism to get the water back in. Why does the water want to come back in? What was the osmolarity as it was leaving this point right here? 100. It was more dilute, remember? If I put a whole bunch of aquaporins, what's the environment out here? 300. So is water going to want to make this fluid in here, this filtrate, the same as the surrounding environment? Yeah. So if I put a whole bunch of aquaporins in place, then as this filtrate travels through, even into the area that has no osmotic gradient, it's just what your normal body is we can make this filtrate the same. And so by the time it arrives here, it still has 300 milliosmoles. All right? We've pulled water back into our bodies because of our dehydrated state. But remember, we're dehydrated. And what we have here is an osmotic gradient. And so if I put aquaporins all the way down, as that fluid begins to come through, what's the water going to do? Stays in the body. So we can create a urine that is heavily, heavily concentrated. Yes? If you didn't hear in the loop of Henle, then you wouldn't have an osmotic gradient to adjust. In other words, you need this countercurrent mechanism to establish the gradient that you can then take advantage of here in the collecting duct. Right? We make it, we use it. Vasorecta maintains it. And that's the relationships. Those are the 3 things right there. The loop of Henle establishes the gradient. The vasorecta maintains it. The collecting duct allows us to utilize it. All right? And it's under control of ADH or vasopressin. Well, it actually starts a little bit before, because this region right here is also subjected to vasopressin. So, as an example, this we can see what happens in the presence or in the absence. It's probably better than my cartoon. And so what we're showing here is our bodies are dehydrated. We want to hold on to the water that we're peeing out just because we already make very, very dilute filtrate. And so by putting the aquaporins in place, water then leaves and goes out into the extracellular space. Now, obviously, if water goes out into the extracellular space, it would begin destroying the osmotic gradient. And so there you have the vasorecta showing you I can take up that excess water and carry it away. That's the maintaining portion. And so what do? Our urine ends up being a very, very high concentration. What started off as being very, very dilute. And we still have a concentration gradient we can take care of. But now you go out and you drink a gallon of water, and so you're now nice and hydrated. All right, it's going to take some time for your body to figure that out. And so you want to get rid of all that water. And so you're already making 100 milliosmoles. You're already getting rid of excess water. So no ADH, no vasopressin. That means no way to put aquaporins into the walls of the collecting ducts. So when the water or the filtrate leaves, it has the osmolarity of 100 milliosmoles. You're getting rid of excess water. So the natural state is to get rid of excess water. Only when our bodies are in a state of dehydration or varying states of dehydration do we have ADH act to cause us to absorb the water back into our bodies. So far, so good, or kind of shaky? Yeah. They're there, so the cell's making them, and they store them away on those vesicles. All right, it's not under the control of ADH to make the aquaporins. The aquaporins or the ADH is a signal to put them into the surface. All right. Now, anyone here ever been told that salt is bad for you? Why? Water retention, which results in hypertension, high blood pressure. Right. Okay. Very intuitive. You understand that concept, although there's now, just saying, there's more and more evidence suggesting that's actually not true. I'm not saying it isn't true. I'm saying there's evidence that suggests it may not be exactly true. Just like everything in life, it's all very complicated. But we're just going to pretend for a moment that it is true, and we're going to look at how our body deals with this. All right? First off, we've talked about sodium reabsorption. We understand that sodium reabsorption in both the proximal convoluted tubular and the loop of Henle is basically under a constant rate. In other words, what we're doing is we're looking at the percentage of sodium in the body, and we're reabsorbing that back in based on that percentage. Now, the loop of Henle is doing this actively. It says, I want to reabsorb 200, or I want to create an osmotic gradient between the tubule and the surrounding environment of 200 milliosmoles. And if you go and watch that video that I described, they'll talk about this. But the number is not important. But you're actively pumping out at a constant rate how much sodium in the loop of Henle. Sodium is being pumped back into the body through the process of reabsorption at a more or less constant rate, trying to maintain a particular concentration. All right? It's the distal convoluted tubule that has no role with regard to percentage. Here, what we're going to be dealing with is we're going to be dealing with load. Load tells you how much salt you have in your body. All right? So what we can say is like this. When we're talking about the proximal convoluted tubule and the loop of Henle, what we're trying to do is we're trying to maintain a balance between water and salt. Right? There's a perfect relationship between those two things because they're the cute couple. Right? Perfect relationship. That's the joke. Yeah, I know. You didn't have to laugh. It's just y'all looked at me like it was like, yeah. All right. So, if I eat a high salt diet from now until the day I die, all right, my body is always going to be reabsorbing salt to maintain the proper water-salt balance by ratio. But in terms of actual number, how much salt I have in my body, I would be extra salty, right? That's load, all right? And when we talk about the high salt diet and how it's bad for you, this is the part that we're talking about, the part that can actually be regulated through the distal convoluted tubule. The greater your sodium load, the less salt you're reabsorbing, all right? That should make sense. I already have plenty of salt. You're extra salty. So, as my load goes up, I'm going to want to reabsorb less and less and less. Now, if you go back and flip a couple slides back to Tuesday or so and look at that sodium reabsorption chart, it actually gives you some percentages. Something like 67% of your sodium is reabsorbed in the proximal convoluted tubule, 25% is in the loop of Henle, and then it's like 10% or some other small value is in the distal convoluted tubule. Yeah.
I'm so confused. In the picture, it looks like even cells either occupying the fluid or it's going back into the plasma.
Well, you can
There's no mechanism where you can create that cell, but you have cells go through. So there's no way you can see it out.
no. Sort of. Right? Because there is a way to pee it out. Distal convoluted tubule says, wait a second, you have too much salt. So we're not going to reabsorb it. We're going to let it go. But what's that salt relative to? The amount of water you have in your body. So if I go take a block of salt and shove it into your body, first you're going to be very mad at me. But you can only get rid of it. Basically what your body's going to do is say, wait a second, there's way too much salt here. How do I balance it out? If I put too much salt in my body, how do I balance it out?
That's why when you drink seawater accidentally.
And that's why you don't drink your urine. Bear. Right? If you don't drink salt water, you're putting water and salt into your body, but it has greater salinity or greater osmolarity than your actual balanced water-salt balance. And so what you have to do is you have to find more water to balance out the salt. Now your body's going to get rid of that excess salt, right? By basically saying, all right, distal convoluted tubule, no reabsorption. Don't worry about it. But the majority of your reabsorption is taking place in the proximal convoluted tubule in the loop of Henle. It only makes up a very, very small portion. And so what ends up happening is that the way you balance out that excess salt is by diluting it out. And when you dilute out water, or dilute out salt with water, your water volume goes up, your pressure goes up, and what do you have now? Hypertension. All right? Now this is the math that everybody understands, and this is why everyone says salt is bad for you. All right? Yeah. Aldosterone? Yes. Yes. And that's what we're going to be looking at. All right? So this is what I was saying. Sodium load correlates with ECF. All right? With volume. All right? And this is all going to be regulated through a big, fun little system, the angiotensin-aldosterone system. It's not terribly difficult. We're going to start, RAAS is renin, angiotensin, aldosterone, and then the S is system. So there's 3 hormones that are involved. Now remember what we said, the distal convoluted tubule plays a role in looking at the salt concentrations in the filtrate. Remember we talked about that, and we said macula densa cells are sitting there going salt, 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 and if the salt levels get too high, then what does it do? It affects the pressure, in the afferent and the efferent arterioles, right? Causes vasoconstriction, vasodilation. We talked about that on Thursday last week, remember? Vaguely? Yeah? All right. Well, those cells that are regulating and marking the salt, what they do is they basically act on these granular cells, and the granular cells not only cause the change in pressure, but causes the secretion of renin. All right? So renin is a hormone produced by the kidney, and what renin does is that it goes and travels in the blood and is going to act on other hormones. Now, ultimately, its job is to change sodium reabsorption. All right? So when blood pressure drops, this is when it's going to be secreted. When blood pressure drops, that's going to say we need to increase the rate of sodium reabsorption. Because if we increase the rate of sodium reabsorption, who follows? Water. Right? And if blood pressure drops and we add water back into the body, then the blood pressure is going to go back up. So that's ultimately what we're going to try to do. All right? So what it does and how it does this, so if this is the big picture, the way that it does this, it acts through a plasma protein called angiotensinogen. Now, angiotensinogen is a plasma protein. It's circulating all around, and it's an inactive hormone. And renin is the enzyme that converts angiotensinogen into its active form called angiotensin 1. Now, angiotensin 1 is converted into angiotensin 2 in the lungs. Now, angiotensin 1 plays a role in regulating blood pressure, but we're going to ignore it because it has nothing to do with the kidneys here. Angiotensin 2 plays a role in activating the secretion of aldosterone. You're going, well, why all these steps? Because they do other things. And what aldosterone does, if you'll recall, is that it increases the number of sodium-potassium ATPase pumps, remember? And so what we're going to do is we're going to increase the rate of potassium secretion, but at the same time we increase sodium reabsorption. And so as sodium comes back into the body, water is going to follow. And so in response to a drop in blood pressure, we've increased the rate of sodium reabsorption by acting specifically on the distal convoluted tubule. We've increased the rate at which water is being reabsorbed, and we've countered the drop in blood pressure by raising blood pressure. Now notice, is this quick or would this takes a long time? What do you think? Long, right? This is a long-term mechanism, all right? If I'm trying to send a note from here to the back of the room, it's going to take some time, right? And that's what we're doing because we have to go through so many different mechanisms, all right? What we're basically doing is we're promoting the movement of sodium back in this direction. So sodium is going back into the body, potassium is going out through the urine, and as a result, water is going to follow. Now, it's easier to look at it this way, all right? And you can see the pattern here. Drop in blood pressure, or basically what we're monitoring is basically a drop in sodium chloride levels, which is an indication of a drop in blood pressure. So that's going to cause renin to be secreted, which acts on angiotensinogen, which produces angiotensin 1, which does its own thing, which we're not going to bother with, which gets converted into angiotensin 2 by the lungs. And then that travels to the adrenal cortex to cause the production of aldosterone, which acts on the kidney to cause sodium reabsorption to go up. And again, you're sitting there going, why so many steps? Right? I mean, if you were designing the system, what would you do? Screw all these steps. I'm just going to make renin do all this. Right? Except angiotensin 2. Angiotensin 2 is a really, really good friend. Angiotensin 2, and it tells you, every one of these tells you in their name what kind of role they play, with the exception of renin. All right? Angiotensin 2 causes the expression of vasopressin. In other words, it acts on the hypothalamus to cause the release of vasopressin from the posterior pituitary. And what does vasopressin do? Puts all the aquaporins in, so where does the water go? Back into the body. Blood pressure goes up. It acts on the hypothalamus again. And what does it do to the hypothalamus? It says, hey, by the way, you know, that loss in blood pressure is also an indicator that you have less water in your body than you really need. So, by the way, you're thirsty. And if you're thirsty, what's going to happen? You're going to drink a soda and increase your blood volume. But you're also putting a lot of salt in your body, so you stay thirsty. All right? But what you do is increasing fluid intake is going to increase water conservation as well. And the third thing that it does, and it even tells you right there in the name, angiotensin, is that it plays a role in vasoconstriction. And if I increase the pressure of my peripheral arteries and peripheral veins, what have I done is I've increased the blood pressure, which counts the whole process. So in essence, using one little tiny molecule, renin, I can act globally to not only increase water absorption and increase blood pressure, but I can act in other ways to increase blood pressure as well. Yeah. Mm-hmm. Because doing one thing isn't going to be enough. Remember, what you're trying to do with regard to the kidneys is you're trying to conserve or preserve water. But even if that's all you ever did, are you still losing water in your body? Yeah. You're not only urinating it out, you're defecating, you're breathing it out, and you are sweating it out. So you need to have a way to replace the water that's coming in. And so by telling your body you're thirsty, you're putting the water back into your body. Make sense? Good. Now, did I promise you this was the toughest stuff? It is. It really isn't, though. All right? RAS is very straightforward. Ultimate goal is to counter what we're seeing here. This is bad. All this stuff down here is good to counter the bad. All right? Now, obviously, when you have a system that turns all these things on, you need to have a way to reverse it. Anything where anytime you have gas, you need to have a brake. Right? It's usually a good thing. Right? And so our brake to this system is atrial natriuretic peptide. This is produced in the right atria, all right, in response to increased pressure. In other words, there are baroreceptors that are located in the atria, and when these are stretched, all right, then what we do is we go, oh, okay, blood pressure's gone up. We got to make sure that there's no renin. Because if there's no renin, then we can have no angiotensin. If we have no angiotensin, we have no angiotensin 2, which means we have no aldosterone. That means we're not going to be absorbing water. We turn everything off, and now we can bring our blood pressure back down. Again, long term. So, RAAS is opposed by atrial natriuretic peptide, or ANP. Good news, on the test, I will never give you an abbreviation without giving you the name, and vice versa. All right? And the other good news is that with vasopressin, I always abbreviate it ADH. So you need to learn what ADH is. Antidiuretic hormone, vasopressin. All right? So atrial natriuretic peptide opposes, oh, look, I wrote it right there, opposes it. So everything that we just talked about over here, it does just the opposite. Now, in those segments that are permeable to water, which segments are permeable to water? Proximal convoluted tubule. All right? Whenever we reabsorb solute, you always reabsorb water. Simple enough. Why? Because of all the laws you've learned since the dawn of time when you entered into the sciences. Osmotic considerations. All right? Solute excretion is always accompanied by comparable water excretion. Always. So even in the loop of Henle, we pump out salt, water comes out the other side to match it. All right? So we always are going to have, whenever we reabsorb salts, we're always going to have solute. But anytime that you lose or gain just water, all right, because we don't have these mechanisms to get rid of excess salt, for example, what do? Well, we're going to be changing our solute concentrations. Basically, we're changing our extracellular fluid osmolarity. Now, that's just a fancy way of saying when I put extra water into my body, then my extracellular fluid becomes dilute. And if I become dehydrated, my body becomes dehydrated. All right? That's all it's saying. And that should make sense to you. So, for example, if I drink a gallon of water, what do I end up doing? How much time do you spend in the bathroom? A lot.